Thank you so much for inviting me here. Good morning, bom dia. I arrived yesterday afternoon and I walked a little bit through amazing Porto, looking around and wondering. And I also started to wonder whether any of you will be here this morning. Luckily, the weather cooperated, so I see that quite a few of you are here, so obrigada for coming. You may also have come because you may wonder, what is she talking about? Did she misspell the name of this presentation? Shouldn't it be data-centric AI? What is this reality-centric AI? I promised to tell you about it. So I'm going to start by discussing what do I mean by reality-centric AI, and then I'm going to delve into a topic that's very close to the topic of this conference, which is related to real-world data. I have a quite long talk, and I'm not sure I'll be able to finish it all, but my plan would be to, after discussing data, which will be the core part of the presentation, discuss how we can complete the ecosystem of building analytics with automated machine learning, but also building Copilot. If I have time, I will also address how can we build using large language models and foundational models code. And I'll say a few words about the way forward. If I do not have time, you will be able to get this talk online, so you can look at the completion of the presentation. So, what do I talk about reality-centric AI? Don't we already have AI that's a reality? We have chatbots, we have a variety of computer vision applications and robots which are transforming the way we live. And we have indeed seen in the last couple of years enormous leaps in AI. And yet, have we seen really a transformation of our healthcare systems? I used to live for 18 years in the United States where the costs are staggering. And now I live in the UK where I cannot even see a GP if I want to. So we have really quite chronic issues in our healthcare systems. And AI, despite its promise, has not delivered yet. But there are other areas, such as climate, or I used to live in Los Angeles, where I would spend hours in a traffic jam. And AI has not really transformed that area, even though I did work on AI for transportation for quite some time. What about the energy crisis? Or for that matter, if a Roman schoolmaster would come back to Porto after 2,000 years, my guess is may not really envision what has happened in the session at the very beginning, which was really quite different than in Roman times. But what they are seeing today, I think in this moment, I think that they would understand as being more or less like a gathering of people discussing a topic. Not much has happened in education in 2,000 years. And what I'm saying here is not that AI cannot get there, but at the same time, I feel AI is not just a few breakthroughs away. And part of the reason is, at the top conferences we usually go to, the NeurIPSs, the iClears, the ICMLs, we see the majority of the talks being focused on data sets that are already predetermined, super clean, and which people do not engage to. This is just a data. So I'm quite happy to see a conference like yours where the focus is on the data making and what's in the data and the messiness of the real-world data, and I'll say a few words about that. Another reason why this data-centric, this reality-centric perspective is going to be important is that numerous predetermined Petri dish tasks are really what we are involving with when we are looking at this data. So what I'm really going to try to propose is that we need to engage with real-world data and real-world problems and try to really solve not just the next algorithm in AI, but rather a real-world challenge with all its complexity and all its messiness. So we really need to orient the AI revolution towards solving the complexities of the real world. So I'm going to argue, and I've argued this already for 2+ years, we need to really have a fundamentally different paradigm for AI, which is oriented towards the realities and complexities of the real world. So over 2+ years ago, I put online a manifesto, which I called the Case for Reality-Centric AI. If you are interested, I hope you will take a look. It's not only a case for it, but also I outline an agenda with various pillars and what I believe needs to happen to really see a transformation around us. In a very brief nutshell, what reality-centric AI is aiming to solve real-world problems and operating effectively and accountably in the real world using real-world data and an AI that is empowering rather than replacing humans. Over the last 20+ years, I myself have worked on a variety of topics. I'm an engineer by training, but I used to do machine learning more or less from the onset of my career. The focus, though, was not the algorithms, but rather trying to solve real-world problems. And over a quite long career, I worked on numerous topics from transportation systems to smart cities, to networking and communication systems, to smart grids. And recently, in the last 10 years, recent for me, I started to look at healthcare and education, which are two topics that I'm absolutely in love with. And I'm going to paraphrase John Tuckey, maybe the world's first data scientist. And the only difference I put there, I changed the word statistician with the word machine learner. So the best thing about being a machine learner is that you get to play in everyone's backyard. So by engaging with these real-world problems that these different domains pose, I've had the opportunity to really look at numerous domains and build AI for those domains. And I'm going to try to compel all of you, I guess most of you here are converted already, that we really need to engage with solving real-world problems, not just building the next algorithm. In the reality-centric agenda, my second pillar is about really building AI that is designed to operate with real-world data. And we often hear that data is the new oil, but like new oil, data has impurities. What do I mean by that? It is usually incomplete. You may have missingness, you may have errors and biases in the data. Data may be costly to acquire and may change a lot over time. Data may also not be accessible to you depending on the domain due to privacy considerations. So one solution that I proposed quite a few years back is the use of synthetic data. So for me, this is a long journey. Now synthetic data is all around us, but when I started this journey more than 8 years ago, there were very few people believing that creating a replica of the real data would be the solution. I'm going to say a few words about the beginning of the journey and what I believe synthetic data can be today, which is really evolving quite a lot. If you are interested to hear what we have done over the last 8 years in this topic, please take a look at our website. So why synthetic data? When we started to look at synthetic data was at the beginning of my journey on looking at building AI for medicine, and I couldn't access a lot of high-quality data sets, and even when I could access them, I couldn't share them with collaborators. And this is due to valid privacy concerns associated with this data. We cannot share such data easily. So how can synthetic data help? Well, we can take real data, we can create on the basis of it using generative models synthetic data, and then we can evaluate the quality of the synthetic data, and this is very important. We shouldn't just generate, but also evaluate how good is the data that we create. And then we can provide this data for a variety of uses, including building machine learning and AI. And after we have done that, we can verify that indeed these machine learning methods are indeed useful for applying them on real-world data for the original data users. I'm going to give you later an example of it. And of course, building synthetic data is itself a machine learning challenge. And we know huge amount of generative models that have been developed by the machine learning community over the years. We ourselves in our lab have contributed to all these different models, from building new strands of generative adversarial models to more recently diffusion models. But this is not just, synthetic data is not only about building generative models, it is also about generating data with the right privacy consideration. So it is a slightly more challenging topic because just generating synthetic data without privacy constraints is not going to be sufficient. I will not talk about that, but we have given over the years a variety of tutorials on this topic, so you can take a look at them. Instead, I'm going to say that we have also built quite vibrant community by building open source synthetic data generation and evaluation library that we call SynCity, that is available to all of you to use. And I was quite pleased that both Google and Amazon seem to be using it. So it's a really quite vibrant community, and I really hope that many of you, if you are interested in this topic, you will contribute to this community. And this is, again, useful both for rapid prototyping as well as creating benchmarks for you if you are a researcher, or if you are a developer, you can use these methods easily and accessibly. Some of these methods that I described today, as a matter of fact, all of them are in SynCity, so if you are interested, you can take a look there. Before I'm going to delve into the new frontiers of synthetic data, let me just anchor ideas by showing you some results from a paper that is going to appear very soon, where we took some of our models, and you see there a variety of models. 3 of them are coming from our own lab, the ones that are performing well. We always show good results for our past work. So you see a variety of models, all of them with privacy guarantees, different types of privacy guarantees. PATE-GAN has differential privacy, while ADS-GAN has GDPR-type privacy, so a very different type of privacy. And what we try to do is we try to create a synthetic data version of the UK Biobank, which is a very powerful and extensive resource, a complex resource, which is very often used to build analytics for the healthcare industry. And hence, we wanted really to see if synthetic data has matured enough in the last couple of years to really allow us to do that. And we indeed see that we can produce very realistic cohorts for this data. And what's also interesting is that the promise that we started 8 years ago seems to be really fulfilled even in this current situation. We took synthetic data, we created on the basis of this synthetic data analytics using an automated machine learning method I'm going to talk more about later, autoprognosis. We created a predictive model, and then we compared it against a very recent predictive model, which is often used for lung cancer, and we compared it one-on-one together with our collaborator, which is a public health doctor, and we indeed saw that synthetic data is indeed fulfilling the promise that we originally intended it for, create privacy-preserving synthetic data that is realistic enough and high quality that we can build analytics which can then give back to the data owners. But today I want to move beyond privacy. This is what initially motivated me when I started 8 years ago to create synthetic data, and we created this synthetic data revolution. But since then I start to believe that synthetic data is more than a second-rate copy. It is a first-rate creation. Synthetic data can do things that real data cannot do. I'm going to argue it is even better than real data. And the reason why I believe that synthetic data is a cornerstone for reality-centric AI is that it enables us to turn unfair data sets into fair data sets. It enables us to augment data sets. It enables us to transfer data from one domain to a very different one. But also it enables us to build simulators, thereby trying to understand and simulate how future would look like, or different types of uses of this data would look like. In view of time today, I'm going to talk only about one of them, augmentation. But if you want to hear more about the rest, please either take a look at our website or see one of our tutorials. So we already know that augmentation is key. You see here a paper that I like a lot from a group that is using medical data and augments it using GANs to create a variety of data that's augmented, and then they are training a predictive model on the basis of this real and synthetic data, and they show that the performance improves a lot. And we saw such examples quite a lot in the last years, and we have not only seen them in imaging, we have also seen them in natural language processing. And the reason we really can augment both imaging and natural language processing very well, it is because we can exploit very effectively the inductive biases inherent in this data. So for instance, for imaging, we can shift the data in ways in which it do not influence the meaning of this data that we are seeing. But what about tabular data, which is ubiquitous in the industry? That is a lot more challenging. So while for images and text we have invariances such as translation for images and temporal translation for text, and associated with this very powerful inductive biases, for tabular data we do not have that. So it is a lot more challenging. And it is tabular data that is ubiquitous in both medicine and education. So we really wanted to understand what can we do here. So what we try to assume is that the data generating process can be described using some form of a relational structure. You often see in tabular data things such as knowledge graphs, or some type of knowledge or semantic type of graph. So we said, well, what if we are assuming that somehow such an underlying semantical structure exists? Let's assume that we don't know it. We could partially know it, we can completely know it, but very often we do not know it. Could we assume something like that and learn more effectively to do augmentation for tabular data? And this is what we did in a paper called Goggle. You can see my students are really quite creative with names. So what we did is we assumed that we have a relational structure in the form of a graph that encodes the functional relationship between the variables. And we are going to have each variable being determined by this specific functional relationship associated with the neighborhood in the graph. And we are also going to assume that there is some semantic encoding there, so there is a sparse and compact representation of this data generating process. However, we are not assuming that this knowledge graph or this semantic relationship is known. It could be, again, partially known, I'm going to talk about that, but we are assuming that it is not known in advance, and hence it needs to be learned from data. So what we did in Goggle is we are learning the underlying relational structure in the form of a graph, and we are going to learn a generative process that is respecting this graph, and we are going to do that jointly. So what we decided to do is to use a variational autoencoder where we have a graph that we are learning simultaneously with the autoencoder, and we are having a message passing neural network as a decoder, and we are going to gradually generate synthetic data through numerous rounds of message passing. For the rest, the VAEs are trained quite conventionally with an elbow loss. And what we do at the first stage, we are jointly learning the relational structure and the generative model. In this way, the generation respects the sparse graph that we are learning. If, on the other hand, we do have some partial knowledge about the semantic graph that also allows for easy injection of such priors, this was actually a challenge prior to Google. We didn't know how to introduce whatever the experts, for instance, in the clinical domain knew about these variables. They often have partial knowledge about relationships, and there was no easy way to provide these inductive biases to our data-generating algorithms. But now, because this graph is already learned, we are able to inject this knowledge in the graph generation. And finally, we are going to be at runtime, after this has been learned, we are going to be able to generate synthetic data, including synthetic data for augmentation. This achieves quite good performance. I still feel we can do a lot better. So part of the reason I show this to you is to show we made some progress, but we need your collective intelligence to advance this field. Not enough has been done for generating synthetic data for augmentation for tabular domain. And I hope more ideas will come. Okay, and the performance really improved quite a lot if you know something about the semantic relationship between these variables. What about the augmentation in the ultra-low regime? This is actually a very challenging and important problem. In my lab, I have a brilliant PhD student that comes from South Africa, Nabil Sidat, and he was very interested to do something in conjunction with clinicians in South Africa, but we discovered very fast that there is very little electronic health record data that we can use. So what we were interested in, what happens if we have very few samples? We have maybe fewer than 200 samples. We cannot even learn anything with a generative model if we have very, very few samples. What can we do? Can we use somehow this type of available data to do better? Can, for instance, large language models help? So in a paper very much led by the brilliance and the vision of Nabil, we built very recently something that we call curated large language models. And this is a recent paper from ICML, where what we did is we used this very limited data we have. And what we used it is to generate, using large language models, tabular data. But large language models, like all generative models, tend to generate a lot of data that is not realistic and is not correct. So what is a key ingredient in this work is a very careful and very principled curation step. And in this curation step, what we are doing, we are fusing the learning dynamics that we are learning on the basis of this real data with uncertainty estimation, thereby being able to create this very principled curated data set, which we then use for prediction tasks. So this enables us to build this type of augmentation for tabular data in the form of this curated data set. Again, this is the beginning of an agenda, and I hope you will engage with it and you will help us do better. But I think trying to understand what we can do in tabular data settings in this very low sample regime is very important. In a conference called Data Makers, we should have solutions that enable us to do something in this very realistic frontier, small sample data regime. Often, actually, my clinical collaborators will come to me and will say, I have this fantastic data set. I collected a lot of variables, but I have only 100 patients. So this is really a real-world challenge that I hope we can conquer together. Another issue is not only creating data sets for use in machine learning, but also better testing our models. Even Google, which is one of the big giants of this field, has been plagued by failures when they built models which they thought were amazing when tested in the lab, but then when they took them to the real world, they failed. And I don't try here to pick on Google. I think this is true for everyone. So what I'm going to argue is that another reality-centric problem we need to engage with is how can we better test our machine learning models? In conferences, in the top conferences that I usually go to as an academic, I am appalled by how little we test these models. And then when practitioners are taking our models to the real world, they often fail. So they are very disillusioned. So if we want to make a difference in AI, we really need to build more robust models that are going to stand the test of time and the test of reality. So we need to evaluate better our models. And I'm going to argue that we need to take a little bit of a look at the industry of aviation, where they would not want to put people in a plane without a wind tunnel, where they tested every component very carefully, as well as the entire product. I think we need to test much better machine learning. We do not need yet another algorithm. We have millions of machine learning methods. I often try to convince my students not to build the next diffusion model, but rather to focus how to use ideas from synthetic data, including diffusion models, to build more realistic and more robust ways to test machine learning models that are very brittle. So what I'm going to show to you here is some ideas on how can we use synthetic data to better test our models. We've done quite a lot of work in this area. I'm here highlighting just one of the works, but I really hope much more will happen in the community. So first you may ask, well, what do you mean? We have holdout data set. We can test our models on the holdout data set. Well, if you look at real data, often real data may not have enough of what we really need to test robustly our model. For instance, you see here a minority group, Black elderly people, who are very few. So the chance that you are going to have this Black elderly in your testing set is very small. So even if you do a very poor job for them, you will declare success, and you shouldn't. So I'm going to argue that we need to think much more about for what are we testing this model? For what subgroups of people is this model going to be used? And also, how will the data change over time? As COVID has shown, things evolve over time, that we have shifts and drifts. And hence, we need to think about that when we are validating and testing our models. So reality-centric testing is key, and synthetic data can help. I'm going to give to you here an example. It's called free-S testing. And free-S testing is using conditional deep generative models to create synthetic data sets, not for training, but rather for validation and testing. So what do we do? And free-S stands for synthetic data for subgroup and shift testing. So what we have is we have limited real test data for small subgroups. And what we do is we train a conditional generative model on this real test data set, conditioned on this minority group. Then we are generating synthetic data conditionally. And finally, we are doing very powerful model evaluation that enables us to really see the performance of the model, not only for the majority class, but also for this minority subgroups. And this enables us to select models that are going to be of high quality, again, for everyone, not just for the majority. So what we are doing, actually, we are able to generate this synthetic data to be able to stress test the machine learning models that we are building for a variety of examples that the user or the people who try to deploy these models are going to envision the use of this model in the short run, but also in the long run. And this is important because, as you will see in the next part of the presentation, where we have AutoML machine learning models, we need to select the best model for everyone. I talked about synthetic data. I mainly talked about augmentation, but I'm very excited about synthetic data beyond augmentation, as I mentioned, for simulation and more. And this also fits nicely into the data-centric AI, a topic that, again, my lab is doing a lot of work on. And together with Nabil, again, we put together a manifesto paper that we call DC Check, that again I hope you will engage with, which is not a solution, it's a framework of thinking about data. And data not only as an input, but also data for training, data for deployment, and data for testing. And it is really the power of data that can empower every single bit of this ecosystem. And synthetic data is just one piece of this bigger ecosystem, but an important one. Again, if you are interested to hear more about our view on data-centric AI, there is a tutorial online that we gave at NeoRIPS last year together with Nabil and Isabelle Guion, who is a Google Research. Fine, we have, let's say, high-quality data, but what about analytics? I'm going to argue that it is very important that machine learning is not only useful for the data scientists and machine learners among us, but rather for everyone, including non-experts. I would love to empower my clinical collaborators to build their models and be able to not rely on a data scientist or a statistician to do that. I'd like to outsource myself, because in the process, they are going to be able to build powerful ecosystems for healthcare, thereby transforming the healthcare system. The reason we have not seen yet this transformation in medicine is because we have this conundrum, this split between the AI world, the statistical world, the data science world, and the expertise world, for instance, the clinical world. And too little is happening. We need to really empower the experts in other domains to build their own methods. And for a long time, I started to work on AutoML. Initially, I thought that this is the solution. I'm going to tell you why nowadays I believe this is no longer the complete solution. But initially, I thought, okay, if I have the ability to choose among these different models for a variety of tasks, prediction, classification, time to event analysis, time series models, causal inference, and if I can automate it all, things will be solved. So I built machine learning that builds the machine learning methods. So I did a lot of work early on AutoML, and together with Frank Hutter, we even started a conference on AutoML a few years back. And really my vision was that we need to build automated machine learning models that build this predictive analytics at a push of a button for experts. Not only models, but as Rich Caruana is going to tell you, very importantly, also model explanations. And over the years, we did a lot of work on AutoML, again, more on our website. Our first model that we built, one of our first models that we built was able to build risk scores at the push of a button. I really was trying to empower my clinical collaborators to take a data set and then build entire pipelines that deal with missing data, errors in data, feature selection, prediction, as well as calibration, would build ensembles out of it. Through meta-learning, would learn from other data sets and would issue these predictions and explanations. And indeed, our success was quite good. Here you see some of the few examples where autoprognosis has been used over the years, including the first model that has been used in the UK using machine learning for COVID-19. We predicted using autoprognosis hospital beds, and we did that only 2 weeks after the pandemic really started to take off in the UK. Since then, together with a clinical collaborator, Professor Eoin McKinney, we built a second version, which is even more powerful for clinicians and a lot more apt for clinicians, and this is available online. This is not only for the clinical world, this is for any type of risk prediction. So if you want a very powerful and robust ecosystem for risk prediction, I really would recommend you to look at autoprognosis. And why AutoML tools are so important is because they allow for easy access, open source. You can use it for a variety of reasons. Also, you may be able to learn using it the value of information. So it's not only about powerful predictions, it's also about what information is minimally needed to issue these predictions. So for instance, by using Autoprognosis 2.0, we discovered that actually for lung cancer, you may need only 3 variables to make predictions using autoprognosis, as opposed to current statistical methods that are using 18, and hence nobody is using them. So that's another very powerful way of engaging with these models. It is a wrong belief that you need more variables for machine learning to take off. No. As a matter of fact, at times, statistical models need a lot more variables to be at the same level of machine learning. But also because things are changing. The data is changing, the variables may be changing, machine learning models may advance, so AutoML is a great ecosystem to keep up to date with data and methods. And again, together with a clinical collaborator, we wrote quite a lot about the power of using AutoML. And for a long time, I thought this is the solution. So why don't we all build predictive models using AutoML? Well, it still requires quite a lot of expertise. You cannot go to if you're a data scientist with some knowledge of Python, it's very easy for you to use autoprognosis. And some of my clinical collaborators, a minority, are able to do that, but the majority cannot do that. Very fast, I realized that there are issues with the data, there are issues with the entire ecosystem that you can easily solve if you are a data scientist, but not if you are a clinician. So more recently, we have built a virtual partner together with large language models that encapsulates some of this AutoML framework to make it, for the first time, really easy for everyone, including people who have no coding expertise whatsoever and no data science expertise whatsoever to build this type of models. So, what you see here is in Climb, we have clinicians, but it could be anybody else, comes with, to Climb with a particular data and a problem, and they can partner with this copilot, which is empowered by data-centric tools as well as automated machine learning tools to really build together with the clinician not only a predictive model, but also visualization, also interpretability, and finally a summary report, which can be used to summarize everything that has been done. Again, we put quite a lot of tools under the hood to enable this copilot. And what you see here is a little bit of a glance on the exploratory data analytics. We have a dashboard on data transformation. There is a lot. Unsurprisingly for you who are working on data, the biggest challenges associated with using AutoML for non-experts are issues associated with the data. There are all sorts of issues that clinical data sets and real-world data sets have. They are not the sanitized data sets that machine learning is used to. And after all this data wrangling is happening, again, through a conversation with the non-expert, but with a lot of tools in data-centric AI under the hood, we are able to build the machine learning models. We compared Climb, again, a baseline GPT model, and again, quite a lot of difference there. One point I'm going to go to, which is advanced memory. We also compared it very recently. We ran a few weeks back the world's first summer school for clinicians. So we did a one-on-one comparison between GPT and Climb, and the majority prefer Climb, and for many reasons, including the visualizations and better presentation and textual responses. But Climb is actually using a lot of large language model coding under the hood to complement the tools. So I want to say a few words in the remaining time about large language models for code generation and beyond. One of the reasons I'm very excited, and I was very excited from the very beginning about large language models, is the ability to really scale up the coding effort. But one of the things that we discovered at the very beginning was that transformer-based large language models are constrained by the fixed context window. So what we built together with a few students in our lab is L2MAC, which is the large language model automatic computer for extensive code generation, which was at the time the first practical large language model-based stored program for code generation, so a von Neumann architecture. And this is what we created. There are many benefits to it, including the fact that we can produce code that is of high quality, given user requirements, and this is very important, for instance, for Climb, but many other products. And what's very interesting is, I think in this architecture, is we build a very good debugger of the code. A lot of code is generated and is not of very high quality, and what was key for us was the control unit and the debugging unit. So L2MAC has a very powerful code check, which is able to correct the code, both for static errors as well as unit tests. And L2MAC was on the leaderboard at the beginning. Now there are other methods, but I still believe one very powerful component of L2MAC is this ability to build robust code generation. Okay, if you want to read more about that, in view of time, I won't be able to tell you a lot, but you can find this on our website, not only the paper, but also a blog and the code associated with it. Okay, this brings me to the last slide, the way forward. So first, I think that data is very important, and I'm very happy to see as many of you here, because I think it is in the data that the future of AI and of reality-centric AI lies. And it is not only AI models which are able to use the data, but also are able to simulate future data, are able to predict possibilities of future data, as well as future uses that may lead to different types of data. So I think the focus will be on dynamic and adaptable systems that can handle a variety of issues and impurities associated with the data. So we need to build next generation AI systems that are engaging with this real world data, and not data of today, but data in which these systems will need to operate, hopefully for many years to come. Also, I'm very big on AI for everyone. If it is for us to really transform the world for the better in medicine and education, but also other fields, we really need to provide enhanced accessibility of these tools to non-experts. Automated machine learning is part of the puzzle, but that's not enough. I think building these powerful co-pilots such that we empower the clinicians and other visionaries to envision the future and build these future systems without us being the bottleneck, I think it's important as well. And finally, I'm really believing that we need enhanced decision makers across a variety of industries, not only medicine. So I really think that in the future, AI may be embedded everywhere, so we need to make sure that this is human empowering rather than human replacing, something very important to me, but also an AI that is proactive and is dealing really with the situation at hand, rather than a current reactive way. But in the moment we are becoming proactive, and AI will make more and more decisions and will take more and more of the decision-making at hand, we really need to make sure that this is aligned to our goals, and not only aligned. I'm very much into not only AGI, but rather empowering AI. So we need to think about the role of the human into this loop and in this proactive loop. Thank you very much.